So what you're going to hear tonight is a story of what we've learned about Mars in particular, how we perform these biological tests, and my own private interpretation of whether we have conclusive evidence or not. Now, I told you I'd start back in 1968 because that's really the birth time of the Viking project. At that time, I had worked already 7 long years trying to get a project going to Mars. I had gone through the ups and downs of 3 sweeping experiences trying to get, they were called Mariner missions or Voyager missions before, trying to get a Mars program put together. I was working with Jet Propulsion Lab then. And finally, in 1968, NASA decided it wanted to, I was working for Caltech then. NASA wanted to have a Mars program. We didn't have a name, Viking, that came later. And the idea was to send a spacecraft to Mars, you land on the surface, to perform 2 things. One, to get some pictures back. Of course, you have to land in order to do that. And secondly, to see if we couldn't do some sort of test for life. As a result of a lot of science, a lot of fighting, a lot of infighting, a lot of politics, and certainly a lot of money, this mission began to grow. It grew almost like a snowball. It grew and it grew and it grew. In a sense, for a very good reason. If you go to all the trouble of getting a spacecraft 400 million kilometers from the Earth successfully on Mars, you want to do as much as you possibly can. You don't want to have gone there with minimal payload. You want a maximal payload. It's sort of like you going on a trip somewhere, a field trip or a vacation. You want to do everything you can. If you're lucky enough to have a trip to Africa, you don't just want to go to Karachi and back. You really want to see everything there is to see. You really want to try to experience a lifetime. And in that same way, we wanted our mission to Mars, we knew that they won't come very often, to be as ambitious as possible scientifically. We wanted a broad brush across all the sciences if it were possible. And as a result, we've really done 13 investigations on Mars, dealing with meteorology, with chemistry, with seismology, with geology, with biology, with atmospheric physics, picture taking, anything that anybody had in the nature of an idea that could possibly be squeezed on this spacecraft was squeezed on. What happened, of course, is the cost began to escalate. And being a civil servant, and since I pay taxes the same way you did, I watched with grave feelings as I watched the Viking payload grow. At the same time, the cost began to escalate, trembling for fear of the fact that somebody's going to come along and cancel it. And in fact, it did get canceled once. Literally, we lived through a hell during the Christmas of 71. When for about 6 days, the Viking literally got canceled. And then, fortunately, the right people went to the right people, and they canceled other things, and they put Viking back on. It was going again. To give you a feeling for numbers, because I really do want to talk later on after you've heard about the science. Many of you asked a question about dollars. But I'm going to try to put this in perspective, because here you have an opportunity to hear more than just science. Since I work for the government, and I spend your money and my money too, incidentally, I have a knowledge of why does it cost so much to do this kind of mission. Viking cost $1 billion. That's an enormous amount of money. By anybody's standards, even, it doesn't matter what kind of a millionaire you are, $1 billion is a colossal sum of money. Most of that money, of course, was spent on people. We didn't send money up to Mars, we sent equipment to Mars. It started out with something like a $400 million project. And as I say, it grew and grew and grew to this $1 billion. Now, it didn't grow sort of infinitely. We didn't have, nobody said, just send as much as you can, the cost is no object. It didn't work that way. We had a budget. And every year, just like your tuition fees going up in ISU. I don't have to discuss money with you, you know that already. The cost of everything is going up. Anyway, every year that something would go up, it really got more and more troublesome. And finally, toward the end, we began to realize that we're now cutting into the bone. We're no longer trimming fat, we're cutting bone. For example, when we talk about cutting payload, or reducing science analysis money, or taking scientists off, or reducing or increasing the risk of landing, those are now serious issues. Now no longer a question of, it would be nice to. When you say we're doubling the risk of failure, now you're not sure whether you're saving is a wise thing. As a result, we finally ended up, as I say, with this $1 billion for the spacecraft. And toward the end, if you're going to ask me some questions about that, I'll parcel that for you. I'll tell you where the $1 billion went. I can't tell you how much came to Iowa, but some of it came to Iowa. Let's begin then in '68 with a growing spacecraft, growing set of ideas rather, that, in fact, we were at that time going to launch in 1973. As you know, Mars and Earth, both going around the sun, you can only launch to Mars at very specific opportunities. And you just can't say, well, today we've got a spacecraft, let's launch to Mars. Mars and the Earth have to be in the right relationships to make what is called the transfer orbit, the transfer of the orbit of the Earth to the orbit of Mars. And that happens every 2 years, because there's a 25-month period between when Mars and Earth line up. So there was an opportunity in 69, 71, 73, and 75, when we sent our spacecraft. There's another one in 77, 79. As you see, they're about 2 years ago. We originally were going to launch in 73. Turns out that we had a budget crunch. And so it's sort of like, you can't afford tuition this year? Well, you'll have to graduate 1 year later. And the same is true of spacecraft. Since we couldn't afford to launch in 73, the budget got stretched out, and we had to postpone it for 2 years. That turned out to be an asset, a liability, because what we could have launched in 73 was not as good as what we would have launched, what we did launch in 75. On the other hand, you can wait indefinitely. Now, the logistics of this thing were fairly simple. You spend from 1968 to about 5 years, 1973, collecting ideas, developing ideas, building some, what engineers call breadboard things, constructing the ideas. Then in 1973 and 1974, costs go up because you start now to build hardware. You really start fabricating the whole thing. Things have to come together as a system. That's the remarkable part of something like the Viking. The Viking is like building, well, a super university. It's all got to come together at the right time. I mean, it's not enough to have the foundations for it. You really have to have a gym, you have to have lockers, and you have to have classrooms and professors and everything else. In that same way, you have to have the rocket ready, you have to have the equipment ready, the people have to be trained, the software has to be done, things have to be tested. And it was during 73, 74, and the first half of 75 that all those events took place in time for a launch in 1975. The window of the launch, that window is the time at which one can launch, was about 30 days. Now, because of the past history of attempts at Mars, namely the Soviets had tried 4 times and lost 4 spacecraft. They had tried to land on Mars and crashed 4 times. We decided we were not going to do it their way. Certainly we weren't going to crash their way. We were going to take a totally different approach to the thing. We took, one thing we did was we sent 2 identical spacecraft. Now, they had sent 4 different kinds of spacecraft, but we decided we want to send 2 in the hopes that one of them will make it. But the more important change that we made is they launched an orbiter, and then they launched a lander. That is, they launched something that would orbit around the planet as the sort of monitoring device, and then they launched something that landed on the planet, hoping that the communications from the ground would get up to the orbit and relay back to Earth. We locked ours together. We married the orbiter and the lander. We sent them together as a package, saying if one of them makes it, they'll both make it. The lander and orbiter are going to be an integral unit. They'll work together just as a married couple will work together. This orbiter-lander combination was then sent to Mars, to orbit around Mars, and at the appropriate time, from a command to the Earth, we separated the lander from the orbiter and allowed the lander to land on Mars. Now, one of the things that physicists will immediately recognize, but most people don't think very much about, is the distances. The distances from here to Mars, you've already heard me say it's 400 million miles, is so far away that literally the time for light to get from Earth to Mars is significant. If we had, for example, if this microphone were plugged into a way of communicating with the moon, just to give you a feeling for distance, and I said, hello, this is ISU moon, the time it took to get to the moon is 1.5 seconds. The time to get back is 1.5 seconds. So there'd be kind of a delay of 3 seconds if we bounced my voice off the moon. If we did this on Mars, not today, but the time that we landed, if I said, hello Mars, this is ISU, the distance is so large, my lecture would be over before I came back. It's 40-minute round trip time just to get a signal there. Now, think about our trying to control the spacecraft. I mean, we say, spacecraft turn right or turn left. 20 minutes later, the spacecraft says, did you tell me to turn right or turn left? Because now I'm in a different place. And you can just imagine the difficulty. Well, it's like driving a car, you know, you turn the wheel and 20 minutes later it makes the right turn. That's the kind of problem. So the solution to a problem like that is basically to build a smart spacecraft. And that's really what Viking was. Viking was, you know, we talk about smart bombs now. That's really the way the spacecraft, it had its own mind. It had, literally, and most people don't realize it, it was a spacecraft capable of carrying out the entire mission if all humanity disappeared. I mean, had we, the whole of Earth disappeared, with one single exception, that somebody has to release the lander from the orbiter. But from that moment on, the whole mission could have been carried out, transmitted back to Earth, and it would have all been recorded here for whoever was around. The point is, Viking was like a small child. It was completely programmed to do its thing from beginning to end. From the time we launched it, it had its own computer. It knew when it was going to approach Mars and what to see. It would know where the ground was. It would know how to release its parachutes and so forth. All that was programmed in it. We had the capability, however, of overriding this. It's in that sense very much like a child. A child has the capability of doing all sorts of things, and what you want him to do is to do all the healthy things like breathing and eating, but not stick his finger in his eye. And so you have to override certain commands. You say, you know, don't stick your finger in your eye. And some children don't stick their fingers in their eye. And the spacecraft had to respond too. I mean, we had the ability to say, hey, don't do that because that's too dumb to do. And the spacecraft, if it got the right signals, would not do that dumb thing. But sometimes, if it didn't hear from us, we'd go right ahead and sometimes do its dumb thing. And our job was, in a sense, to run behind this smart little spacecraft and keep it from doing anything disruptive. And obviously, we were successful because tonight, as I'm talking, there are 2 spacecraft on Mars, 2 orbiting around Mars, all transmitting information. There will be several million bits of information transmitted back to Earth, received at Jet Propulsion Lab from the beginning of my lecture to the end of mine. Several pictures will be taken tonight. Several return signals will be coming back. It's still happening today. All this started, as I said, in '68, was launched in '75, got there in '76. Here it's '78. It's over a year and a half, and this remarkable set of machines are still working. In fact, many people have asked me, how come you're not working on Viking still? You know, why aren't you out there so granular with headphones plugging in things? Basically, I'm worn out. The spacecraft is worn out. People are worn out. Most of us have left that job and passed it on to the next generation. It's a very healthy thing. Usually you think of these things as they did their thing and then they got the glory. The fact is we did our thing and then passed it on to another generation of scientists and engineers who are still have it operating. And it will continue to operate till about midsummer. In about September of this year, we're turning off. September, October sometime. First and early to release that. If you ask me about that, I'll tell you about that. Okay, that's sort of the background of Viking. Now what I expect to do tonight, the rest of the time, I'm going to darken the room, and some of you can go to sleep and some of you can't. And I'm going to let your eyes adapt. I'm going to show you sort of 3 stories. The first story will be showing you the mechanics of how you launch a spacecraft, how you get it there, and what you have to do, what you have to not do. The second story, the big story, will be what did we really find? What did it look like? What was the surface like? What was the weather like? What was the chemistry like? And the last segment will be what did those biologists do? What were they up to? What kind of data did they get back? Does it make any sense? So, Marilyn, if I could have the first slide. Oh, what a beautiful system. Now, if I could just darken this one. I'm not going to dwell on this one. This is just a listing you can kind of peruse. These are the characters of the experiments. Here you see various investigations that were done. Well, I'm the lucky guy who gets to stand up here and talk to you. The fact is, I didn't do these investigations. My job as chief scientist was to see that they got done. I was like the symphony conductor leading the symphony. I didn't play anything. These were done by 70 scientists in 13 teams in universities all over the country. There was a team responsible for taking pictures, another team responsible for studying water vapor, thermal mapping, and you can read as well as I can. A group for biology, another group for chemistry, another group for meteorology, seismology, etc. These 13 teams all over the country converged at Jet Propulsion Lab in the winter of '76, just about this time, and trained for about 6 months, and starting with the summer of '76 began to get their data back. And those teams still physically exist, even though new people have begun to pass through those teams. There's still a meteorology team. It has only one of the original members on it, but there's still a team. So now you see the way the spirit of this whole thing is being brought together. These are, of course, just a list of the instruments. Now let's go on and see a little bit. Next slide, please. Spacecraft is not as small as you might envision. First of all, of course, there's no men in this thing. It has nothing to do with manned exploration. This is a one-way mission of a scientific vehicle from Earth to Mars to return data to the surface. It's bigger, though, than I think many of you think. This is about 3 stories tall. It's about 40 feet across, so it would just about fit inside this auditorium with the solar panels extended. It consists of 2 parts. This upper portion is the orbiter. It's the bus that carries the rest of the air. The lower portion in the capsule is called the lander. And this is the thing that gets released. These 2 make up the spacecraft. This gets released and is directed to the surface. Now, you can't see through the capsule because we had a problem of contaminating the planet. Obviously, if you're going to do biological investigations on a planet, you can't send terrestrial organisms there and expect to get any kind of results that mean anything. So we had to literally sterilize the whole lander. And you'll see a picture in which we take the whole lander, put it in a big pizza oven, cook it for 2 days, and then take it out, leave it in this capsule, send it to Mars, and do not open it until it arrives to Mars. The only thing that actually got onto the surface of Mars was basically a sterile spacecraft. The business end of the orbiter is this guy called a Science Scan Platform. You see the words here. It's about the size of a coffee table, and what it consists of is the 3 instruments that were responsible for looking down at the planet. These are cameras and infrared devices for measuring water and for making temperature measurements of the surface. These are the devices that we used to help us find a safe landing site. Especially after that Soviet experience, we knew that what we have to do is hunt for a safe landing site. And that was perhaps the most exciting part of the mission. Next slide, please. Just give you some feeling for the size of the lander. Here's the lander. It's about the size of a compact car, small Volkswagen maybe. And you see these fellows around it. They're putting it inside of this aeroshell, this biological shield. And you see how they're dressed in this funny bunny uniform. Next slide, please. And here they are pushing it into the pizza oven. This is the last time I saw my love, when it was getting cooked, ready for sterilization. Now, no one had ever done this before to a spacecraft. I mean, no one had ever. Well, think about it. If you took your television set and put it in your oven and cooked it for 2 days, you wouldn't expect it to work. And therein lies the heart of the engineering problems. How do you build transistors that will stand temperatures of 120 degrees C? How do you build elastomers? How do you make lubricants work? How do you make all these sensitive condensers and sensors work? And a good deal of the development of Viking was the development of parts that will actually be heated. Now that technology is useful elsewhere. You know, if you're thinking about spin-off, that's not my favorite game, but if that crosses your mind, that turns out to be one of the major things that we did, because there are many places in industry that one needs high temperature components. And Viking solved an awful lot of that problem. Next slide, please. Here you see it finally, it's upside down, but of course there's no such thing as right side up and upside down to something you're going to launch to Mars. Here's the lander, here's the wings folded down, and it's being put underneath a nose cone. This is 14 feet across the air, about 25 feet high, 28 feet high. And this is then going to be hauled up on top of a rocket. The rocket is called a Titan Centaur and launched to Mars. Next slide, please. By this time, we're down in Florida. Next slide, Mary. Here you see this Titan Centaur rocket. It's 19 stories tall. It's an interesting rocket. It's a combination of a military rocket, the Titan, which is usually used for military things, and a NASA rocket called the Centaur, which is up on top. And we use this for the first time. And here you see this thing being hauled up. Now, life is never as simple as you think it is. This happens to be number 2 being hauled up on number 1. Turns out that The day we were to launch, literally hours before we were to launch, somebody had found a mistake. One of the tiny valves was left open inside this red rocket. A valve about the size of my thumb was, by some error, left open. And it's a guidance valve. And had we launched with it that way, we would have landed in Cocoa Beach. And so the term in space jargon is the mission had to be scrubbed, which means that 40,000 people who came out to watch the launching of Viking went home disappointed. I never saw so much pot smoking and guitar playing that night as I did when 40,000 people came home. Anyway, at that point, all we could do was launch the second one first. So we went back to the hangar, got the second one, took the first one down, put the second one up, and 10 days later launched successfully Viking number 2. And then 10 days after that, we launched Viking number 1. Next slide, please. This is Viking 1 going up. You can't sit through a space lecture without at least seeing some rocket go up somewhere. Beautiful, clear day. Viking 2 wasn't such a happy situation. Viking 1 was a nice, clear day. Viking 2, we launched in the most intense tornado season they have in Florida. And on the heels of the Viking launch, only minutes afterwards, was a 10-day downpour that would have absolutely wiped us out. We had just the luck to launch at exactly the last moment possible. Next slide, please. This is how we communicate with it. Now, if you think about the problem of communicating from here to Mars, one thing is obvious. The Earth is turning and Mars is turning, so how do those guys keep track of what's doing what? This is the antennas that we communicate with. This is the largest movable antenna in the world. This is 64 meters across. This one happens to be in Spain. There are 3 of these antennas. One in California, one in Spain, and one in Australia. And as the Earth turns, obviously, there's always one guy who's looking up at Mars. And what we do is we hand over from station to station, as the Earth rotates, 8-hour segments from Spain to Australia to California. And these movable antennas then tip around and follow the course of Mars. Next slide. Well, Brother, could you go back to that one? Thank you. To give you a feeling of size, this is a car. Enormous thing. I mean, if ever any of you get a chance to visit these things, it's a colossal thing. I mean, 64 meter doesn't sound so. Obviously, most of that time we spent training, fixing up the errors, trying to find houses to live in, fighting with in-laws and so forth. May the 19th was a classical day because that was the time when we had to inject the first Mars mission. That's the day in which we fired a large propulsion engine and allowed the gravitational field of Mars to literally pick up the moving spacecraft. The spacecraft is coming by, you fire this thing and point it the way my arrow was getting pointed, in towards Mars, and allow the gravitational field of Mars to pick it up, and it now forms a new satellite around Mars. Mars now has 2 more moons than it had before. The orbit of this, we set specifically at 1 day per revolution. That is, what we wanted to do is we wanted to go around Mars at the same rate that Mars was going on its own axis. The reason for that is we wanted to stay stationary over one place at the closest part of the orbit. The reason we had this elliptical orbit instead of a circular orbit is it takes more energy to do a circular orbit, and that meant giving up part of the payload. We didn't want to do that. So we accepted this very elliptical egg-shaped orbit, saying, well, it's enough to get close in here. This is about 1,000 miles, 1,500 kilometers, to get into what we call the periapsis, the point in here. This apapsis is about 30,000 kilometers. Both are valuable, but it's obvious when you're close in the planet that you're going to see the most. Next slide, please. So every day we basically came over the same place on Mars. Now, at the appropriate time, when we had discovered what we thought was a safe landing place, and I'll come back to that in a moment, then the idea was to release the daughter ship from the mothership, allow the mothership to continue to orbit around Mars, and the daughter ship will now start on its entry down to the Martian atmosphere. Now, the Mars atmosphere is devastating from the point of view of landing a spacecraft. It is the world's worst atmosphere. The moon is much better. Earth is much better. There's just enough air to burn you up and not enough to slow you down. You could not invent a worse atmosphere to try to get through. And the results are we had to have 3 braking systems. That is, 3 systems of sort of slowing yourself down. The first is on an aeroshell. You see this funny shape of this thing. Well, it's not so funny. It's what you might expect. This aeroshell now begins to tumble, and this aeroshell was used, you'll see in the next thing, turned around so when it hit the Mars atmosphere, it began to move in like a flying saucer. In fact, if you were a Martian and could see well enough, 1,500 kilometers up, you'd see this wild flying saucer come roaring down at 4 kilometers a second, screaming in at you. This represents one of the experiments that we've done. Retarded potential analyzer was used to measure the ions and electrons in the Mars atmosphere. Next slide, please. Here now you see the spacecraft comes screaming in, literally burning up. It slows it down by burning the surface away. As it comes in, it creates an atmosphere around it and actually slows it down. At about 7 kilometers up, 5 miles up, a parachute is deployed. Now, when you're screaming down, now it's no longer 4 kilometers a second, but it's well above the speed of sound. It's a Mach 2 parachute. This is not usually done on the Earth. I mean, we don't have parachutes that operate at Mach 2 at twice the speed of sound. And you don't sort of release a parachute at those things. You literally have to fire it out of the back of it with a cannon. There was literally a mortar in the back of this thing for firing this huge 50-foot parachute out of the back. And now this thing takes some of the energy out. At 1 kilometer above the surface, now the parachute, you'll see, next slide please. The aeroshell has been let loose. The engines start. There are engines, reverse thrust engines. That's the last system. Remember, there was an aeroshell and a parachute, and last there was engines. Engines come down. All the time, there's a radar system bouncing back and forth to tell the spacecraft, I'm here. Remember, we aren't even part of the system. We only find out whether we crashed or landed 20 minutes later. I mean, we're passive in the thing. We're watching the child being born and have nothing to say about it. And so this thing is measuring where the ground is, making all of its measurements, saying, now I have to release the parachute, now I have to start my motors. These retro rockets get fired, the parachute is cut loose, and finally it senses where the surface is and comes to touch down on the Mars surface about as lightly as though you jumped off a chair, because we're carrying scientific instruments. And all these sequences have to happen. Any one thing that doesn't happen, and of course there'd be a disaster. So it was quite a remarkable event, not only to land one, but to land 2 successfully. And if there is a tribute to this mission, to the engineers, it was to build a system capable of performing this remarkable feat by itself. Okay, once it's down safely, now the trick is to start the scientific experiment. And the data gets fed back from the spacecraft, back up to the mothership, which is still circling around the Earth, and from there it comes back down to Earth. Next slide, please. Here you see the way in which we did the interrogation of the surface. Here you see a spacecraft flying by, taking a swath of pictures. There are 2 cameras on board this thing. We are moving so fast across the surface, as I say, at 4 kilometers a second, that you take a picture, and while you're reading that picture up, the travel of the spacecraft continues. And you use a second camera to take the next picture while you're reading the first one. So it's as though you walk across the planet, take a picture, read it out, take another picture, and each time you're taking one, you're reading the other one out. And you see what we did was map a swath, 2 pictures wide, clear around the planet for 500 kilometers. And by taking these pictures in sequence, try to develop a map to understand what Mars is like. Now, the size of the spacecraft is such that a 25-centimeter boulder would knock us out. I mean, a little stool, in a way, would have killed the spacecraft. So there's no way that we could tell what was there at that side. I mean, at 1,000 miles away, there's no way of telling where the stools are. What you have to do is deduce, based upon what you see, smooth areas from rough areas. What we wanted to do is land in an area that was as smooth as possible. It was like looking for Iowa from 1,000 miles away. Think about it. Those of you who've traveled by air, you look down at Iowa. You really can't tell where the fence posts are. You really can't tell where the boulders stick out. That was the problem we were faced with. You're traveling only at 7 miles up. We were traveling at 1,000 miles up. So no matter what sort of telescopes you could use, There's no way we could make any positive identification of rocks. Even if you knew a flat spot, how well could you land on that? You know, we're lucky when a plane driven by a man lands on a runway within a few feet. And here's a little spacecraft landing by itself. All you can do is take advantage of statistics. That is, land in the smoothest place and hope there's not a rock under you. And you'll see the results. Next slide, please. As we approached Mars, this is what it looked like. This is the planet from 7 million kilometers away. This button that you see is the largest volcano ever seen in the solar system. This is Nix Olympica. Nix Olympica is 28 kilometers tall. It's about 5 times as large, or 10 times as large as the largest terrestrial volcano, Mauna Loa. Whole island of Hawaii is one big volcano. This thing is about 500 kilometers across, a huge thing. Here's another set of sister volcanoes. In fact, this whole region is an extremely interesting part of Mars. It's called the Tharsis Bulge. It's literally a bulge. It's like a potato with an eye. This whole thing is bulging out, pushing out from pressure from within. This area is a very recent area on Mars. If you look at the pictures, the close-up pictures, we find very few craters in this area. The number of craters tells us how old something is. The more craters there are there, the older it must be. The fewer craters, the more recently it must have been formed. And here, while you see these large volcanoes, on the fields around the volcanoes, there's almost no craters. So this is a fairly recent upwelling of volcanism on Mars. Next slide, please. This was the first picture. I will never forget it to my dying day, because this was to have been the proposed landing site. When we were still, before we sent, we had all sorts of committee meetings and usual faculty arguments and so forth about where we'd land. And this was the place we had first picked as our candidate site. This was going to be smooth as a blotter, and we didn't expect to see anything. And when I saw all these pimples and dimples, I went crazy. I felt like a teenager at that time. All these things are craters. The picture is 40 kilometers across. So this thing is about the size of Des Moines. And this thing, I guess, is about the size of Ames. And you can see a thing the size of this, the tiniest thing you can see is the thing about the size of this building. I'm going to give you some perspective. What your eyes see as the tiniest little blemish is about the size of this particular building. So when you see something that's rough, it must be really rough on the local side. All those little dimples and pimples and everything are standing up. That's no place to stand a spacecraft, clearly. Incidentally, this little Cheerio you see is a little bit of dust on the camera lens. That's no problem. You erase that electronically. That's easy to do. The thing that made this picture so exciting, though, was the geology of it. You can see these beautiful streamlines formed here. Very, very suggestive of flow. Almost everybody in the audience will say, looks to me like something was flowing by here. And that's what we believe now. We believe this was some of the first evidence we saw of liquid water on Mars. Now, the subject of water on Mars is one of the most interesting things there is. The pressure, the atmospheric pressure on Mars is so low, it's only about 1% of the Earth's pressure, that water doesn't form in the liquid state on Mars. There's no oceans, there's no rivers, there's no ponds. Water acts like dry ice. You know, dry ice just goes from a solid to a gas. Water does the same thing on Mars. It's either a solid or a gas. There's plenty of ice on Mars. There's plenty of water in the atmosphere. But there's no such thing as an ocean on Mars. Yet this looks very suspiciously like the flow of water. What we believe now is that Mars at one time did have flowing water, lots of it. That there were enormous rivers on Mars. That does represent flowing water. And the reason for it was the atmosphere of Mars today is not what the atmosphere was like at the time that this flow took place. Maybe 1 billion years ago or so, there was plenty of atmosphere on Mars to allow water to form. And there was, in fact, liquid water. Now, that's very important to the person, the biologist, thinking about the origin of life. Because without water, we can't imagine, without water in liquid form, how life could form. Next slide, please. So we moved on to look for another region to land. Obviously, we could maneuver the spacecraft, and we kept moving the place where we were thinking of as a candidate landing site from place to place. This was a second site. This didn't look too helpful either, because all this erosion, it looks like leprosy or something. You see this erosion. This is really caused by winds. Terrific winds on Mars are known to tear the surface loose, and what you see is an overlayer of dark material and an underlayer of light material. And this stuff has literally been eroded away. Well, one of the clever geologists, Rob Hargreaves from Princeton, said, look, if that stuff is eroding away, maybe what you ought to do is go find where that stuff lands, because there may be a nice soft pillow there. I mean, if all that stuff is eroding away, if you can only find a nice soft, puffy sand that's getting loose from there, that may give you a nice flat landing site. And that, in fact, is a strategy. And that's what really did it. Next slide, please. On the way looking for that place, we passed this interesting thing. Again, look at the fascinating rivers here. They really are rivers. I mean, at first, when I used to call these rivers, I would be very apologetic. But now geologists have come to accept that these are, in fact, very ancient rivers on Mars. Many people have asked me, are you sure that this isn't formed by wind or lava or something? Aerodynamicists, fluid dynamicists have examined these in detail. While that's not my field, they're now convinced that this is really a liquid that caused these and caused this to happen. And of course, the most likely candidate is water. There's nothing else in the solar system that we would expect in such quantities. Notice how we're beginning to piece the pictures together now to make mosaics of maps. That's the beauty of contiguous pictures that fit together like a jigsaw puzzle. Next slide, please. Here's some more evidence of flowing water. You see what appears to be rivers flowing into this common channel, very much like our Mississippi here. In fact, the geography is right. The uphill is here. Collection basins are downhill here. But one of the questions we don't understand is what happened to the water? There's still an enormous question about water on Mars. That there was liquid water, there isn't much doubt. But what its fate was is not understood at all. Next slide. This is one of my favorite pictures. This is a canyon on Mars. And Mars, I told you there's a colossal volcano on Mars, but nothing like the canyon on Mars. There's a Grand Canyon of Mars that stretches 5,000 kilometers. It would be like a canyon stretching clear across the United States. It's about as wide as the state of Iowa in most places. It's about 6 to 10 kilometers deep in places. And what you're looking at is a cross-section through that gigantic crater. Here's the edge of edge of that canyon, I'm sorry. Here's the edge of the canyon. You see this very old crater that's being eaten away here and falling down. Look at this beautiful, this is called an alluvial fan, the geologist here. The whole edge of this is slipped loose and come down. But from the other side, from the other edge, it's coming the other direction. And the way my fingers cross in the middle, that's the way these two alluvial fans are coming to meet now. Look at the information just in this one picture, this ancient thing forming here, the highlands of Mars here, the young thing, notice the young fan formed down here. Can you imagine what it was like on Mars when that thing went? It may have happened all in one day. We don't know. It may have taken a while to slip. But certainly, geologists call it mass wasting. This whole thing came roaring down. Notice the wind across here. You can literally see where the wind has swept through the bottom of this canyon and carried material out. We don't know where all that stuff went. We simply know there's an enormous gaping hole on Mars, probably caused initially by a fracture and subsequently worn out by the winds. Next slide, please. This is an area near the landing site. And what makes this picture is there's clear-cut evidence of enormous flow of water. Look at these huge scouring of the surface of Mars, piling up of material here, where it cut through, formed a throat across here, cut across the top of these embankment here, and flowed out here. The spacecraft is now resting, Viking 1, about where the exit side is, ironically enough, relative to this picture. Now, this area must be a relatively old area, because you notice after that came these craters. All these things that happened later on. Not these craters, these are the Cheerio marks I mentioned before. That's the same dust fleck on picture 1, 2, 3, 4. You notice it's on the same camera. This camera and this camera are the same. So this pair was taken together. This picture and this picture, and then this picture and this picture. And then the next pass, this picture was taken. Next slide, please. Here's another uniquely Martian phenomenon. This is a crater on Mars. You don't see anything like this on the Earth or the Moon. If you can imagine an object about the size of Des Moines that came in at 50 kilometers a second and hit right here, and literally vaporize the surface and the underlying material. Now, the underlying material on Mars is called permafrost. It's literally frozen water. It's ice underneath the soil. The rock now turns into gas. The ice turns into steam. The whole gemisch begins to move. And what you find is though when you were a kid, you dropped a pebble in the mud, you get a splat. It's literally a splat. And you form this beautiful wall of China around the edge here. This rosette pattern. This motion of the surface is very unique to Mars. It doesn't happen on the Earth, and it doesn't happen on the Moon. For the reason that there isn't the permafrost on the Earth in most places, and there isn't on the Moon. Now, on the next slide, you'll see that that's not the only kind of crater. No, the previous one. Yeah. This is much more like a lunar type crater. Many of you who've worked on lunar photographs will recognize a typical ray crater, where the explosion took place here, but literally threw material out in all directions, and you literally see the rays of material as it came roaring out. Now, why is this different than the last one? The answer is the permafrost here either was absent, or it was so low that it never got that steam mixed with the rock. There was nothing but a big explosion with material being deposited all across the surface of Mars. But that first one was a uniquely Martian type of crater. Next slide, please. This is the humor for the day. One Sunday, I had nothing better to do than to get the Los Angeles Times excited. I said, I think we've discovered life on Mars. The guy here. And of course, they ran it on the front page of the LA Times. Most of you recognize, having seen Mount Rushmore, this is nothing but a very large rock with the sun shining just the right way. The interesting thing was the responses I got. And besides everybody wanted to call it Harry or Mike or Joe, one guy wanted to know how come he had smallpox. So I use this slide to tell you about data. This is actually errors. These little holes are called bit hits. There's like static in the data. There are places where we didn't get any data back. There's where we get our pictures back. We get a stream of information that keeps coming along. And every so often you don't get any information. It's like a telegram with words missing. And so you just make a black dot where that is. And this is what is called poor communication. This is about the worst kind of communications that we got. Mostly we didn't get that very many of these little black dots in it. Next slide. Yeah, it's about the size of Mount Rushmore. This is one of the moons of Mars. This is Phobos. Now, for those of you in science, there's a very interesting article in the last science edition, the one that had the picture of Kepler going on it. That's the subject of enormous debate now. Phobos and Deimos are two natural satellites of Mars. This little one's only 11 kilometers in diameter, but of extreme interest because Mars' moon now, people believe, did not form the same way that Mars did. Many people now have begun to study these moons as sources of interest in what's happening in the asteroid belt. One thing was these funny lines that seem to go across there. And that was the subject of enormous debate for a long while. What causes these parallel lines? Is this caused by scratch marks when this moon is moving around Mars? Is it scratched by big boulders that are sitting out in space? Are they compressional lines? Just what cause are they? Craters that are formed by explosions? And there's still some debate about what causes these parallel lines. Next slide, please. The edge of that is rugged because of the light. It's not really that rough. It's a smooth surface, but what you're seeing is the shadows that are cast. Now, this is the polar regions of Mars. Mars has extremely interesting poles. Most of you know it's white up there, and some of you may realize that we've been arguing for a long time whether it's dry ice or water. It turns out it's both. It's both CO2 dry ice as well as water. And what you're seeing here, we landed in the northern hemisphere when Mars was in the summer, the high point of the summer. And yet there's still polar ice, long fingers of it that extend down to about 65 degrees north latitude. This is water ice. This is not dry ice. The water ice is left long after the permanent CO2 caps have gone. And what you see here are the long fingers of water ice. There's a tremendous amount of water ice on Mars. The Mars atmosphere, just to give you some sort of feeding for numbers, has about, well, if you took all the water in the Mars atmosphere and condensed it into one big ice cube, you'd end up with an ice cube about 1 kilometer on the side. There's about 10,000 times that amount of ice in the pole of Mars. Next slide, please. This is also these are called laminated terrain, and you see the steps, just like the set of steps that follow the edge of the polar ice cap. Next slide, please. From an artistic point of view, I thought that was very lovely. This is a dust storm forming. This was the time in which we could no longer communicate with the spacecraft because the dust storm had gotten so much, we couldn't take pictures. We could communicate, but not take pictures because this dust storm began forming. And we literally couldn't see the surface. It was like a wintry day over Des Moines. And you're trying to land to give a lecture. Next slide. Now here's the lander. Obviously this is not the one on Mars. This was the one we kept. We kept one at Jet Propulsion Lab. And before we would ever try changing this little child's mind, we would try it out on the sister spacecraft. This one is sitting on a bed of sand with a painted background, Mars in the background. This is a meteorology boom. It's measuring the temperature and the pressure and the wind. This thing is a claw. You see an arm here and a claw, very much like my hand. Here you see the 3 feet. You notice there's no power system here. At least there's no solar system. There's no place to plug the spacecraft in on Mars. So we had to carry nuclear power supplies, and that's the thing under here. Plutonium power supplies that operate on 35 watts of power. The heart of the machine is inside. That's the chemistry and the biology experiment. And the idea was to extend this claw out, pick up material from the surface, retract it, drop it into the spacecraft, and perform our experiments. The cameras are these 2 large things. We have 2 cameras on it, and the cameras can scan around 360 degrees. This is the antenna for obviously sending the information back to Earth. Next slide, please. This was the first picture. Now, I'm sure everybody in this room saw this picture today that was printed. The register must have carried it. There must have been any number of publications who saw it. This was the first picture that man ever saw of the surface of Mars. You have to appreciate that this camera works by taking scan lines one at a time, like a bunch of fence pickets. It takes scan line after scan line after scan line and puts them all together and makes a picture. The first thing we saw was the edge of this. And when I saw this fellow's heel print, I got very excited. And then I saw the brain coral here. And I saw the bicycle path here. And you can imagine the biologist reading into everything he saw. I think I see life on Mars. Well, obviously these are mostly rocks. It's a scene that looks suspiciously like California. And many people accuse us of maybe taking pictures in California. I assure you this was taken on Mars. The picture is remarkably good. This is the spacecraft. The foot of the spacecraft is about 18 inches across, and it's 1 feet. Notice the hole in the edge. And those of you who are sitting close, you'll see a beam of light that passes down through the hole and shines on the shadow. I'll get the sun's way. A little square here. It shines on the shadow of the spacecraft. For the first guess at taking a picture, think about it. If somebody said to you, I'm going to take you out somewheres, land you somewheres, and you have to preset your camera and take 1 picture, how lucky you would be if that were the quality of the picture you got. Next slide, please. Lucky guess on that part. This was the first color picture on Mars, and many of you have asked the question, why is Mars red? It is red because it's rusted. That's literally the simple scientific explanation. It's iron oxide on the surface of Mars. We don't know how thick the coating is on each of the grains, but literally if you were standing on Mars and reached down and picked up and rubbed it on your face, you'd turn red, just like rouge. And I'll show you a picture of the spacecraft that literally has red stuff all over it. The sky has surprised us. It's pink. We didn't expect a pink sky. We expected a black sky because the atmosphere is so thin. It's pink because it scatters the sunlight. All this red material that's sitting up there as little particles scatters the sunlight and gives us a pink sky. Next slide, please. Now the camera began to pan around and take pictures. Here you see the meteorology boom in the way, taking a picture of our own arm now. And here you see a big rock in the way. The rock we ended up calling a Big Joe. And here's some sand dunes. Now it doesn't look so much like Northern California, it looks more like Southern California. Big sand dunes and big rocks in here. And you can see close, a little from the far, you can see some of the layering of these sand dunes. May I have the next slide now? Here's a closer edition of that. Isn't it remarkable to be seeing a picture of Mars as though I was showing you a good Polaroid shot of someplace in the California desert, and yet you can see with the clarity the events that take place here. But obviously, and here's an important point, no evidence whatsoever of anything suggestive of life either in itself, footprints, rat holes, anything. Nothing at all in any of these pictures. An important statement to be made. Most of us believe now that we saw no visual evidence for life on Mars in those two landing sites. Next slide, please. Later on, I'm going to show you this rock again. Remember my telling you, had we landed on something as small as a stool, it would have knocked the spacecraft off. This is about 5 meters across. I'm sorry, about 3 meters across and about 2 meters high. So had we landed 15 meters farther to this side, there'd be no Viking 1. You can see how many big jagged boulders there are. And we were lucky, we landed among them. Almost exactly vertical. And you could have landed with almost any angle, and yet we sat down almost exactly vertical. Next slide, please. Now this is obviously a picture on Earth. This is the arm. I'm going to show you a few pictures of how this arm works. It digs into the soil. It's about the size of my hand, clamps up, retrieves. This whole thing is drawn back into the spacecraft, and then dumps its material by inverting the arm and then shaking it out of these little salt and pepper shaker holes. It shakes the fine material out so that we can get the fine material that we're missing. Next slide, please. Here you see attempts, once we got pretty good at picking up material, you see the arm is going out here. I may have inverted this picture. And it's actually pushing rocks apart. Yeah, I think the picture is inverted, but we'll leave it that way for the moment. We literally move material away. We're doing rock rolling on Mars. Next slide, please. This little pair of eyeglasses is actually an experiment. Those are little magnets, the shape of eyeglasses. When we sent this out, there was no black thing on here. It was colorless. There were just 2 little colorless magnets. And by digging down into the surface and watching what magnetic particles stick to it, we could tell something about the magnetic qualities of the surface material. Mars has about 4 to 7% magnetite, maghemite in its surface. Next slide, please. For the geologists, I thought I'd include a little chart of what the various compositions are. Most of you know from reading the journals that this stuff all exists in the December 17th issue of Science, for those geologists in the audience. I don't expect to make any other comments about that. Let's turn now to the biology. Next slide, please. Oh, just 1 or 2 more pictures that are important. Here you see we were digging into the surface. The question was, were the results on the surface the same as if you had dug underneath the surface? And so we got our digger out and we started digging into the surface of Mars. And you can see, at least from visual experiences, that the red stuff goes at least to as far as we could dig. We were digging down about 1 foot here. Next slide. This is Viking 2. We'll run through some Viking 2 pictures. Surprisingly similar kind of scene. The rocks now, though, are much more porous. Here the rocks are much more dominated by volcanism. You can see the porous character of volcanic type rocks as the gases bubble out. Next slide, please. You can see landing in this place with a spacecraft. Well, this isn't even a place for a bicycle, let alone a spacecraft. Clearly a very hazardous site. Next slide, please. And here you can see how big some of these things are. It's a closer picture. Next slide. Notice how evenly spaced the rocks are. Now here's a pair of pictures that are extremely interesting. Here's Big Joe. Jonathan, could you focus this a little more? There's an area right in here I want you to see. Something dramatically happened. In this region, you notice here's the Big Joe, or the big rock, and then there's a smaller rock here, and in between it, kind of an area of sand. Now, next slide, Marilyn. Notice now something's happened. Here's the same big rock, the original rock, and something has happened right in here. You go back to the first one and keep focusing it. Here's the original picture with only the 2. And now the second one. Literally, the scene of Mars has changed. Now, why is that important? The fact is, we don't know anything about how old the scene is. This happened within 50 days after we landed. We don't know whether this is caused by some kind of a jarring of the planet, whether it was wind that caused it, but the fact that it happened is important. Mars is changing literally before our very eyes. If in that short 50 days it could change that much, can you imagine how it must have changed in a year, in 1,000 years, in 1,000,000 years, in 1,000,000,000 years? It must be that Mars is changing fairly rapidly if it changes that much in these few months we were there. Next slide, please. In Maryland, if you sharpen it for this white stuff that you see here, that's right. In the lee of all these rocks, literally it had snowed on Mars. Those of you who live here will recognize more than Southern California what's going on. There's been a deposition of, we believe now, water ice around the rocks of Mars. This happened during the winter of the season. The other picture you saw was the summer, and now we're seeing winter. What we're really seeing is literally the seasonal events on another planet. That's never happened before. Never seen that on the moon. We didn't even suspect this could happen on Mars, and yet here's very clear-cut evidence. I don't think the snow comes down as snowflakes. I think it deposits and simply piles up. But it's very dramatic evidence of the importance of water to the planet. You notice how we've got all sorts of color charts and targets for looking at things. Next slide, please. This is a Martian sunset. This is the last of the pretty pictures. The sun is down about here. It's casting its glow up, illuminating the sky. In the next slide, you'll see what scientists do. They sometimes take the TV and they turn the color up. This is the same picture, and you notice the dramatic reds that begin to appear. This is sort of commercial. This is the cover of Science if you go looking for some of these data. The cover of Science, December 17th last year, looked like this. A year before that. Next slide. Now, I'm going to show you something about two key instruments, and then we'll close. One instrument is the organic analysis. Now, why is an organic analysis important? And the answer is, to a biologist, the very substance of life, we believe, is going to be organic. We thought there would be organic material on Mars because many of the meteorites have organic. And since Mars is close to the asteroid belt, meteorites are expected to come from the asteroid belt, we certainly expected to find organic on Mars. The biggest single surprise of this mission was not finding life, but was not finding organic matter. We were looking in the range of parts per billion. Now, on the Earth here, not only is there no place that has much more of that, but it's hard to even make a place. If you build a laboratory and if you build solutions, if you try to purify solutions down to the level of purity of having less than parts per billion of organic material, you have to build a whole facility. Here we landed a spacecraft, used this machine, this is a gadget called a gas chromatograph, mass spectrometer. And what it does is it takes a sample of Mars, warms it up, passes it through a column, and then snips the sample the way your nose would snip it. It does it on a molecular level. That's what the mass spectrometer does. And tries to measure the organic material. And we found no organic material on Mars. That was a great surprise, great shock and a great surprise. Because while we expected maybe we wouldn't find life, we surely expected to find this organic matter that came from meteorites. To this day, that's one of the most perplexing questions. And maybe in the question period we can bring that up again. Next. Now, I'm going to just show one or two slides of this and then close here. This is the biology experiment. Remember I told you we biologists had our go at it. There's no such thing as a single litmus paper test for life. And there's no sort of, you can't go out and buy a life detector. Nobody has to do that here. The closest thing on Earth to that may be germ warfare or something, because there's so much life here, we don't have to detect it. What we were trying to do is perform rather simple experiments on the surface of Mars that would be interpretable. Basically, what we were looking for was growth, or respiration, or photosynthesis, or some sort of basic commodity of living things. Now, we did 3 experiments represented by this cartoon. This one I would call the terrestrial type experiments. It's exactly what you do if you're looking for life on Earth. We took a solution of nutrients. We laughingly called it chicken soup. We mixed up a nice rich combination of all kinds of goodies and, from the biological, bacteriological laboratory. And we dumped it on the Mars soil. And what we were trying to do is measure respiration. We did the same thing when you go to a doctor's office and he measures your basal metabolism and hooks a mask to your nose and you breathe in and breathe out and he measures the oxygen disappearance and the carbon dioxide buildup. Well, that's what we were trying to do, but we did it with more gases. We measured nitrogen and hydrogen and oxygen, all the gases you could think of. We were trying to find out, is there anything in there that's consuming any of this stuff? And I'll show you the answer to that in a moment. Because Martians may hate terrestrial soup. I mean, you can just imagine the Martian sits there and he looks at this awful stuff and says, my God, who would eat that junk? We decided maybe we can't guess what Martian food is like. maybe we'll just have to assume that Martians eat their own stuff, whatever that is. And in this experiment, we did what we call a Mars type experiment, where we added nothing. We gave it sunlight, that's the little bulb here. We gave it Mars sunlight. We gave it carbon dioxide gas, which we know is on Mars. That makes up most of Mars' atmosphere. And we simply allowed photosynthesis to take place. Now, we did a crafty thing. The carbon dioxide we labeled. We attached carbon-14. It's sort of like putting a label or a marker on the carbon atoms. And we followed the path of the carbon atoms as they would be developed into the organic material if there were photosynthesis taking place. It would be as though you took a green plant and gave it its normal carbon dioxide, put a little label on it, and followed that label as it got built into the green plant as a result of photosynthesis of the green plant. In this other experiment, I like to call this experiment the liberal experiment. It makes a few assumptions about Mars, but not too many. It doesn't use a rich gamish soup like this one. It just uses a few simple compounds. It doesn't depend on Mars. It sort of helps it along a little bit. Here, a very few simple compounds were added, and the idea was to follow respiration again, respiration of metabolism, to see if we could get the Martian bacteria, if there are any there, to kind of eat our stuff and breathe out carbon dioxide. And again, we use the radioisotope technique for following the course of this. Now, next, I'm only going to show you this experiment and this experiment. The last one is a little complicated and all. I'm going to avoid that, but I'll tell you what the answer to that is. When we get the answer to all of them, this one was a definite negative. No question about it. We did not discover life at that point. We did, however, discover something astonishing. When we did this experiment, we discovered the surface of Mars is highly oxidizing. It's as though the Martian surface had a kind of Clorox type of stuff in it, bleach or something. Extremely oxidizing condition. When we did the experiment, enormous quantities of oxygen started coming out. No one expected this. To this day, we don't understand where all that oxygen is coming from. In this experiment, there was what looked like, in the first blush, a real positive. And I tell you, those of us who had spent so much of our life doing it, we were trembling with excitement when the first blush experiment came in. Because the first time we got what looked like a real positive. We tried to repeat that positive 7 times and never were able to repeat it. Now, to a scientist, the inability to repeat something is disastrous. And that tells you just don't know what happened the first time. You can't believe a single positive result when you get negatives. And to this day, that's the results we're stuck with this experiment. We've got one experiment that I would say looks like a positive experiment and 7 negatives following. And because the question of life on Mars is such a serious one, I mean, you just can't be casual and say, well, we think we've discovered life on Mars. You really have to commit to feeling that I believe I found it or I believe I haven't. Most of us now believe this experiment did not find life on Mars. That first positive was due to some chemistry that's going on Mars. One explanation is perhaps the retro rockets caused some kind of chemical reaction, and that's easily explained in the experiment. It's this experiment that got most of the attention. And I'm going to show you the data to this particular experiment because this was the one that half the biologists said looked like it was positive and half the biologists said it looks like it's negative. And to this day, that's where we sit. And I'll show you those. Now, if you'll skip the next slide, Marilyn, just go quickly through that. Oh, well, okay. I'm sorry. Reverse one and then skip this one. This is what the machine looks like. This is a biological laboratory. This is, in a sense, the most expensive machine ever built by human beings. This is in the order of $60 million to build just one machine. Now, so we'll skip the next slide, Marilyn, and go to the next page. Skip that and go on. Now, what you're looking at, I know most of you aren't scientists and you don't like it when somebody shows you graphs. I'm going to explain. This is a relatively simple graph. This is time going along here. This is days. We call them sols. We have to have another name because Martian day is a little longer than Earth. So this is 1 sol, 2 sols, 3 sols. This is a week of sols. This is 2 weeks of sols. We're sort of 2 weeks on Mars. It's the investigator's name. Up here is the response of biology. That is, if this were a flat curve, there'd be no biology, no nothing. On the Earth, I want you to ignore this wiggly stuff. This is engineering data. It's interesting to an engineer, but not to a scientist. On the Earth, if you didn't have any biology, this would be a flat line, as I say. If you had biology on Earth, this thing would begin to go up and continue to go up. Now, what you see is the thing started off like a bomb. It really looked like we had something. Then it tapered off and stopped. At this point, we decided, maybe it's run out of gas. Maybe something's happened here. Maybe we got to give it another shot of goody. And so we gave it, here you see, second injection. What we expected to happen was the thing to take off again, the way it did here. Instead, we got a result we have never seen on the Earth. Instead of taking off again, it literally dropped. You can see the drop here. And to this day, the investigators are not able to duplicate this drop in the curve. Now we said, maybe there's something funny about this thing. Let's give it another injection and see what happens. May I have the next slide, Ron? Here you see the first injection. We waited and waited and gave it another injection, and it dropped again. I mean, that's Mars. That's the way it's behaving. In fact, we did this experiment 5 times, and every time it behaved exactly this way. That's a uniquely Mars kind of experiment. Whether it's chemistry, biology, whatever is happening, that's real. That's not just sort of some fluke. Because every time we did it, it would go up this way, then drop when we gave it another injection, and drop when we gave it another injection. We tried what biologists call a control experiment. We took the same soil, and this time we tried to kill the bacteria and repeat the experiment. What we did is we heated it for 3 hours to 180 degrees C, and then repeated the same experiment. If you get the same response, you must be dealing with some sort of funny chemistry. But if you've killed the biology, you ought to get a flat line. Now, on the next slide, you'll see the data that we got. And there's the flat line. We obviously had destroyed whatever was causing it. That's what divides the biologists. Some biologists say it looks to us as though you're dealing with a biological phenomenon. Most biologists, however, are unwilling to accept that. The reason for that is they say, true enough, this looks like a typical way of killing biology. The trouble is that there's too many kind of chemicals that will behave the same way. And you really can't, on the basis of this one kind of experiment that doesn't behave in an explainable way, in the positive sense, you really can't go around saying there's life on Mars. You simply haven't proved it. Now, that's enough for the slides, Marilyn. Thank you very much. You can turn that projector off. Let's get some lights back in here. Let me conclude. I'll tell you what I think my own view is. I've exposed you to some data. You've obviously seen that Mars is an interesting place. Anyone would give an eye cheek to go there, come back, and not lose too much time over it. But as far as life is concerned, I think that we haven't found it. And that's my own private view. Some biologists would disagree and say, well, the evidence looks interesting. And that's as far as they'll go. They won't say that we found life. They'll say the evidence looks interesting. It looks suspiciously like biology. But the question of life on Mars isn't something to be casual about. We can't be wrong on this. This isn't something, just think about it. The science fiction writers, the kooks in the world, the TV dramas, the people who are looking for a little green man under every rock, you can't be wrong on this issue. There's too much at stake. All science, in a sense, is at stake. Because if we, the scientists of the world, say, yes, we think there's life on Mars, and then have to eat those words a year later, science as a whole will get a very bad reputation. Those scientists really don't know what they're talking about. That's the trouble in a good deal of science today. It isn't that we can't expose our points of view. We should expose our points of view. But here's an issue in which taking a conservative position is almost necessary because of the impact that it will have on society. The question of life on Mars isn't just a biological question. This is a social issue. This is one that deals with the philosophy of mankind, the theology of mankind, the way he thinks. And as a result, most of us as biologists feel we've got some extremely interesting evidence of oxidation on Mars, some interesting curves that are very hard to explain in terms of chemistry, but not convincing enough evidence of having discovered life on Mars. With that, I'll leave you with my mission. Thank you very much. People with babysitters can be excused because I know what it's like when you've got things at home. I'm obviously going to answer as many questions as you want to sit for, but don't feel badly about getting up and leaving if you have exam tomorrow morning, sitters that have to go, you're just plain sleepy, or any other reason. I won't feel hurt. Those of you who want to stay and chat about money or politics or some of this data, I'm delighted to answer questions as long as you want. Yes?
Is there any fear
I'll repeat all the questions.
is there any fear that the Russian spacecraft, which I understand weren't as well sterilized as ours, caused contamination?
Okay, he's asked an interesting question. Since I've already told you the Russians have gone 4 times, and he said, how about the Russian spacecraft? Have they been sterilized enough? Do we suspect maybe that caused contamination? There's sort of 2 parts to that. First of all, the Russians did really sterilize their spacecraft. We and they have an international agreement. At least we believe they did. We don't know that they did. We both have an international agreement with all nations of the world that anybody who sends a spacecraft to Mars till 2018, it was made in 1968, this thing, for 50 years, until the year 2018, will sterilize the spacecraft. The idea being by the year 2018, we ought to know enough to one way or the other decide. But, so the Russians have really taken this, as far as we can tell, seriously, and have gone through the motions. Now, if the Russians tried and failed, because their methods were different, we heat sterilized it. I have no question that our spacecraft were sterile. I mean, I personally went and watched them put it in the oven, and I watched the pressures and made sure the gases were all flowing, no bacteria and so forth. So I know what we did, and I would stake my reputation on it. We don't really know what the Russians did. We know what they said they did. And it is possible that they didn't do everything they said they did. On the other hand, contaminating a whole planet is pretty hard. I mean, even if they did land some bacteria on it, and that's possible, the chances that we picked it up, and we landed in the other hemisphere, that we picked it up 4 years later is very small, especially since there's no organic on Mars, or at least none that we found. This absence of organic, as you can see, has me climbing up the wall as a biologist. I am very troubled by that. That's the thing as a biologist. It stands like a giant roadblock in my whole way of thinking about life on Mars. No matter what data I see, I keep thinking, where is that organic material? Now, there may be organic on Mars. That's an interesting aspect. It may be that it's there in these very small amounts. It may be that it's up in the polar regions. After all, all my statements are based on only a couple of handfuls of stuff. Only 2 little locations. And here I am generalizing about a whole planet. I didn't mean to carry on with your question. But I think my concern about the contamination is not serious. My concern about our sampling is very serious. I mean, I'm not sure that we really know Mars based on just these 2 little areas.
What similarities or dissimilarities did you find from looking at the Soviet pictures of the Venusian surface?
The similarity between the Soviet picture of the surface of Venus as compared with the Mars surface. They really only released 2 pictures of those Venus shots. And I had the lucky occasion recently to be in the Soviet Union where I really saw firsthand the best editions of those pictures. And I'll describe what I saw. It's as though you took a large piece of concrete and slammed it down very hard, and it broke into many fragments. There were many, like a dish, like a platter would break, flat cracks, not cracks in the surface, but cracks in this rock. We saw nothing like that on Mars anywhere. I mean, I think the surfaces really are different kinds. They're formed different ways. The surface of Venus is much hotter than Mars.
You know, when I read the big surprise was that the ability to view the horizon, because Venus was considered a really cloudy, the huge surface on it.
True enough. The pressure on Venus is considerably higher than the pressure on Mars. It's carbon dioxide, and people didn't expect to see very much. Venus is encased in clouds, and people thought maybe we wouldn't see anything. But in fact, they had a good view of the surface and a reasonably good view of the horizon. Now, those pictures that I saw, and they claimed they were the best, looked as poor as our worst. I mean, this isn't a boasting of we're better than they, because obviously they have their good points too. But from purely an ability to take pictures, there's no question that those Venus pictures were very inferior to anything we saw in life. Yes.
Can you speculate on the reason for the rather uniform distribution of both?
Well, I'll give you what I think is the geologist's interpretation. He's asking a question about the uniformity, especially in Viking 2. All the boulders seem the same size. Why is that? That's kind of funny. And the answer that the geologist gives me is, when this volcano went off and exploded, there was literally a separation. Little stuff going one distance, and little size stuff going another distance, and big stuff landing closer in. And what we're seeing is that The crater that we think caused that is called Mi, M-I-E. And what we think is when this Mi went off as a huge volcano, that size sorted out well, I guess like wheat shape or sorted out, happened to end up in that particular region. As its atmospheric sorting by size. That's the geologist's explanation. Yes.
Are you involved in the payload planning proposed 1984 mission to Mars and can better biology to redesign that won't create the uncertain results?
He's asking whether I'm personally involved in planning the next payload and whether a better biology can. In a sense, yes, both those questions. First of all, we don't believe there's going to be an 84 mission, unfortunately. I wish there were. Remember I told you there were 2-year intervals, and I ended up with 71, 75, 79, 81. It happens to slip then to 84 because you go from December to January, and 86 and so forth. And until recently, maybe 6 months ago, there was hope that maybe an 84 mission could be ginned up. No hope. The money isn't forthcoming, and NASA's made a category statement that it won't do an 84 mission. 86 is still possible. 88 is possible. It's every 2 years. I'm involved in the planning in one sense and not in the other sense. Right now, we're not selecting the payload yet. We're really trying to develop the logic and the science behind it. One of the things that, if you'll open my briefcase, I want you to hold up. You open that briefcase, you'll find that JGR edition. I want to show you what the product of a Viking looks like. What he's going to hold up is an edition of Journal of Geophysical Research. That's a big, thick, 1-inch journal. That's the product. There are 51 papers that were put together. Yeah, that's right. Just hold it up high so they can see the cover. Those of you who get interested, I'm leading this in the geology department. Anybody wants to see it or read it, Dr. Richardson will have a copy of it. And I think, Bert, I think you have a copy too, don't you? I think Dr. Nortley has it. You have a copy also? Yeah, okay. So there'll be at least 2 editions floating around, and eventually the libraries will get it. That's our product. I mean, that's what Viking is all about. Viking is an attempt to try to build knowledge, and these 51 articles represent. Now, the future payloads really are based on what's in there. The answer isn't in there, but what data we have will dictate what the future payloads. They'll, in a sense, be self-selecting. I'll privately be involved in the sense of saying, yes, this is a better one than that one. But basically, I won't be the one who says, we have to do meteorology, we have to do biology, we have to do this. That's dictated by science. As far as biology is concerned, there is now already a genuine effort in improving on the biology that we did, both in refining the experiments that we had and trying to pick up some new ones. And I would solicit any ideas of anybody who's got a better idea for things to go. And one of the things that people have asked me is, how about a microscope? Why don't you send a microscope to Mars? That sounds like a neat idea. That question hurts me to the quick, because that was my experiment. My thing didn't get to go. That's the way it's like. I mean, you compete. It doesn't matter whether you lead something or not. You have to be on an open competitive footing. And a microscope simply wasn't, we couldn't develop at the time, couldn't develop it right for this mission. So the next mission might have a microscope on it. Good idea. And I encourage anybody to look for new ideas, especially in biology. Yes?
Yeah, I have 2 questions. First one, referring to your last slide, could it have been possible that some kind of life could have been preserved over the years, and you may have been close to the environment that it was adapted to, but it died out in the beginning?
Okay, I'm going to rephrase your question and then answer it. He's either trained in biology or he's thought about biology, and he's saying, is it possible that life is, we use the vegetative stage, not in the vegetative, maybe it's in the spore stage, maybe it's sitting there immobile, maybe it's sitting there kind of asleep, hybridized or something, tiny bacteria. And what we did is we suddenly brought it to life. We gave it a shot, just hit it with the right stuff, and it began to come out, maybe it didn't come out all the way out. Sure, that's the kind of thing we thought of. That's the only explanation I have. If somebody said to me, there is life there, there really is life there. Now you've got to explain the results in terms of being life. I'd say the reason we don't find organic is there's just not that much organic around. That all the life that's there is in a spore form. It's sitting there waiting for its ice age to end and the new age to begin, maybe a million years from now. And Viking arrived and happened to catch these spores at just the right time, and we saw this little burst of thing. That would be a reasonable, it doesn't violate any scientific principle. It still fits common sense, and it fits, sort of a biological kind of explanation. That's possible. The thing you have to consider is, just because something is possible, as you know as a scientist, that isn't necessarily the explanation. You really are forced to look for more concrete evidence. And that's the next experiment.
Okay, and I think I read somewhere that the brain, like the Lander, had a vocabulary of 20,000 words. How did you come to use these words?
Now, if you're talking about the program for running the Viking, no, you have to make one more statement. You said it had 20,000 words?
A vocabulary of
Oh, I see. Well, no, it doesn't work that way. What he's saying is, he read some words that the Viking had a vocabulary of 20,000 words. How do we have to pick the words? It really doesn't work that way. I mean, it would be nice, and obviously you're reading some writer who wanted to poetically put it that way. What it has is, it has a certain quantity of information. It's just like any other programmable computer. It has a certain quantity of information, commands, based upon what it has to do. Now, there's some things it has to do, some things it would be nice to do, and some things after all the other business is over, then you can do it. It's just like your own life in a sense. It has to land. I mean, that obviously has to come first. So the first priority stuff is do everything you have to do in order to land. Secondly, you have to take a picture. At least one picture has to come back sometime. Next of importance, you have to send back the entry data, the data that you got on the way down. And so these things were prioritized. The last thing it had to do was maybe do the little magnet experiment, try to take a picture of where those magnets were. So we prioritized things. And what we did is select things up to the computer's work, full computer's work. And certain things didn't get done. Until after we got control of it, then we could clean out that network and say, we've already landed, we've already taken the first picture, we've already done the entry science. Now we can ask the computer, we'll load up the computer and say, take this, and take this, and take this, and take this, and program another set into it. And to this day, we are still sending commands up saying, well, we've looked at the weather now for almost a full year. Let's turn our attention to seismology. Instead of just taking little 10-minute segments every hour, let's look for a whole day of seismology. Let's just look at seismology all day long. And so we're able now to get this educated computer to do things for us that we otherwise wouldn't need. Yeah.
Has there been any recent attempts to get the seismometer on the first Lander working again?
Yeah, he's hit it nice, and there's the man who's been reading. Of all the 13 experiments on each spacecraft, there's one that didn't work, and that's the seismometer on Viking 1 did not work. Now, I don't mean it didn't work, I mean we didn't get any useful data on it. The way you build a seismometer is such that there's a rocker in it, a very sensitive rocker, and you have to cage it, you have to hold it when you're launching it. Obviously, you can't launch with this thing rocking back and forth, and you cage it. And when it gets to Mars, then you've got to free the cage. You burn through a wire, and you free the cage, and then it's all the lock. We got all the way to Mars, tried to burn the wire, and it's still caged. Viking 1, it still has a cage thing. It's working fine, it's just not giving us any data. The seismometer is there, it's just telling us nothing is wrong. And we have tried now to burn through that wire, I guess about 6 times, and there's still 4 or 5 more attempts at it, and nothing. My own belief is we're never going to get any useful data from that seismometer. Now, we have gotten data from the other seismometer, and some you win some, you lose some.
Something along the political line. Do you believe that there will be any further attempts at hard landings, soft landings on other planets? And do you think the Mars again before any other planet?
No, I have to know more than that. When he's asking me about what is the plan, the program, the politics, the strategy, what sort of things are planned. Let me tell you that, first of all, we really don't know an awful lot about what the Soviets do. We sort of have about a 2-year knowledge of what they're doing. I mean, they're very good about telling us. I mean, they will tell us, we're not going to talk about it. I mean, there's nothing you can do with flat earth. Or they'll say, we're going to talk about it, and this is what it is. My point is, they don't lie to us. What they do is they refuse to reveal what they reveal. Right now, they have no Mars thing they're about to launch. We know they're not going to launch before 1984. That's a statement of fact. We don't know. They might use the 84 launch opportunity, but they're not going to launch in 79. They're not going to launch in 81. And they could go on later on. We know we're not going to launch to Mars before maybe 86 would be early. We have no official, yes, we're going to do it for Mars yet at all. I mean, NASA simply does, it has a lot of things that we wish it could do, but nothing. We have one, as I think you may know, on the way now to Jupiter and Saturn. We have a plan for a Jupiter probe, something to go down into Jupiter. And we have a Venus Pioneer, which is going to Venus. That's all the things that are on the book. After that, everything depends upon what the results are. In general now, which is really the thrust of the question, the general attitude of planetologists is to explore the outer planets before it does an extensive job of Martian investigation. Despite the fact that Mars is very exciting, very interesting in a geological point of view, from a biological point of view, has an atmosphere it's like Earth in many ways. But that said, we know very little about the outer planets. And the next obvious thing to do with Mars, there's obviously two important things to be done. One is to put wheels under a spacecraft. We've landed in only two little places, and the frustration of seeing day after day after day the same scene would drive you into distraction. You'd love to just get up on your toes and see what's over the horizon or move over there. So one of the obvious things to do is to put a rover on Mars and move. The second thing is to bring a sample back to Mars. That's the one place we know we can bring a sample back from the moon. And NASA in general feels it would like to do that sort of the end of the 80s and 90s, sometime in that time period. But getting a sample back to Mars will be worthwhile. Now, getting a sample back to Mars, first of all, it's not easy. It's not cheap. And what's more important, there's a question of biological hazard. While many of us feel it's not dangerous, there's the fact that you just can't breathe.